My name is Wenjuan. I'm a researcher and project lead in data science team of Wageningen Food Safety Research. So I'm very happy to be here to present on behalf of our research team here. I listed their names also below, so they are all contributing to my presentation slides. So as you can see in the title, what we are trying to do is to develop AI-driven prediction models for emerging food safety risks using a holistic approach. So what we are doing within Wageningen Food Safety Research, we are having two different types of tasks. The first one is using structured data to do prediction models, and the second one is to use unstructured data like text data to develop a knowledge graph. I will start with prediction model parts. I think this figure gives you a very good overview about what we are going to do with prediction models. So here I want to emphasize the importance on the drivers of changes, which Nina already gave a very good introduction on that. So I'm not going to bother with details parts with what is the drivers of changes, but just explain what we are going to do with the drivers of changes in our model. So you see on the left top, we have monitoring data on food safety hazards. And what we want to add into our model inputs is data on the drivers of changes, which is directly or indirectly causing food safety hazards to occur. And what we apply is using a set of machine learning algorithms that could capture the patterns in the data that eventually could allow us to predict food safety hazards occurrence in the future. So I will start also with the data parts because to make good models, we need good data. Luckily, we have access to the EFSA monitoring data. So for the ones who are not familiar with EFSA monitoring data, is a data file contains 29 European countries plus United Kingdoms across many different food products and also contaminants with millions of measurements. And in this data file, you could find information on the product contaminants, concentration of the contaminants, and also information on the sampling country and also country of origin. After in-depth look into the data, of course, with machine learning models, we need to have a data set that has enough data for our model to get trained. So we zoomed in the use case as prediction of pesticide contamination in dry lentils. So lentil is one of the HOLiFOOD supply chain we would like to work on because it's a new protein, like plant-based protein for the upcoming future. And you see that within the pesticide category, we have 6,000 out of 765,000 records, which is about 0.8% records has a measurement value, which means that the majority of the records doesn't have a value. What does that mean? It means that the machine cannot detect the residue level of the pesticide in that sample, which means for us it's negative samples that is safe. But only 95 of the records out of these 6,000 actually have a value above legal limits. So you see that the data is highly unbalanced in a way that it has most of the data that are negative samples, but only a very small amount of data that is positive. So to make our model data a bit of more balanced, we use tens of MRL. MRL is the maximum residue level, which we use to classify if a sample is contaminated or not. So if it's above MRL, then we classify it as positive samples. So we only use tens of MRL in that case for the create more positive cases. And for the pesticides, we use aggregation methods because how it works with pesticide detection is we have one sample and we are going to run about 500 to 1,000 pesticides measurements on this one sample. But in our model, we do not distinguish the specific type of pesticides because we don't have enough data to train. Instead, we only classify if one out of these 500 to 1,000 samples is turns to be measurements is turned to be positive, then we classify this sample as positive with pesticide residue. So this is about the monitoring data parts, and let's move to the drivers of changes data parts. So within HOLiFOOD, we also have work package that is work package 5. Where our partners is also works a lot to define those drivers of changes. So what they did is they conducted a very extensive literature review, and they also performed a Delphi study with the experts. And in the end, they derive a list of drivers of changes that we could use as inputs for our model. So to select which drivers are applicable for our case, we have 4 criteria. The first one is it needs to be available with data, and it also needs to be relevant to the lentil supply chain. And the second one is we want the data to have a global coverage so that it allows us to link to the country of origin parts. And also we want to have a good quality data and from reliable data sources. So you see this is a table where they listed these 14 drivers in the end from the Delphi study. And 10 out of these 14, we were able to have a good data sources linked and reflected in our data inputs. So here is a general overview about what type of drivers were included in our data. So you see on the top, all those indexes are kind of socioeconomic or political indexes reflecting how well is a country doing with their governmental effectiveness or regulation. Besides that, we also have drivers that are linked to logistics performance or the quality of transportation with regard to different transportation mode. On top of that, we also have economic data on the different farm or agriculture inputs, and also pesticides prices, and like the ratio between organic fertilizer and synthetic fertilizer, just to reflect the circularity in the production as well. And we also have data from like consumption to represent how this dietary change is happening with regard to the new proteins. Last but not least, we also have data on this NDVI and agriculture stress, which is using satellite image to derive an index to reflect how well is a crop growing at the field level. So on top of those drivers, of course, we also have data from climate parts. So in the end, after all the data cleaning part, we have 1,700 data points with 437 features. As you see here, actually, we tried different ways of separating the trained data and the testing data. So the ones we are currently working with is using the years, which means before 2019, we use it for training, and after 2019, we use it for testing. We have tried a variety of models in our data sets, ranging from basic ones like support vector machine type of models to XGBoost that is very good with classification methods. And also we also tried deep learning based models. Those models are very good with coping with large feature spaces and finding these hidden patterns within complex relationships between the drivers. And of course, we have these 300 features, which means that we have a lot of features for the model to make decisions on. And to be able to make more effective decisions, we of course have to do this dimensionality reduction. We started with principal component analysis, and we also tried like using autoencoders to map the features into a smaller decision space. But eventually those ones were not being effective in our specific case. So we end up with using feature selections, which means that we use the most important 61 drivers for the model inputs. Since our data is highly unbalanced, we also applied this SMOTE technique, which is synthetic minority oversampling techniques. So what does this techniques means is basically create synthetic data to kind of create more weights on these samples that has a very that is minority in the data. So we created it for both output label and country of origin. So for output label, what we mean is we try to create more synthetic data on the positive cases. And for the country of origin, we mean that we also create on the bit of more synthetic data on the country of origin where they had only a few times food safety hazards detected. So this is our current model results. The best performing model is this support vector classification model. After small resampling strategy and feature selection, you see that the recall is relatively decent. So it's 85%. What does that mean? It means that 53 out of 62 positive cases were being able to classify it correctly. But you also see that precision is not good. It's only 25%, which means that we still have 156 cases classified as positive, but supposed to be negative. So we have a lot of false positive in our case. Here we have a feature importance table. I'm not going to go for in-depth here because of the time reasons. But what I want to pinpoint here is that we want to have these most influencing features selected that could be used to explain the occurrence of food safety hazards. So in this way, in the future, we could monitor those trends of these features. So, for example, we could apply anomaly detection on those features, or so to say, the drivers of changes, and we could come up with suggestions that could be used in the future risk-based monitoring program. So next to the prediction model within Wageningen food safety research, we are also working on the knowledge graph parts. What is a knowledge graph? That is a structured representation of information that occurs, that captures relationships between entities in a way that allows us to do intelligent querying, inference, also get a good understanding. So in these graphs, you normally see is that we have entities which are the nodes, so the circles in the graph. And those can be enriched by, for example, like food products, hazards, or processing steps, just to name it. And we also have relationships which are the edges in those in this figure you see. And the edges can be enriched by, for example, like contains, contaminated by, or supplied by. So this is a concept of knowledge graph. How did we build our graph? So we actually, because of the release of the large language models, we start to move from a manual labored way of populating this graph to using large language models to populating the graphs. What we do is we use abstracts from the scientific literature, and we put those abstracts into the large language models. And we do prompt engineering, and we ask for the food entities and food safety contaminants. So what we get in the end can be, for example, you see in the first column parts, you have maize contaminated with aflatoxin. And then we are going to match those entities with URIs, that's the unique identifiers used in ontology context. So for the food items, we use food on. Specifically, we selected food EX2, which is invented by EFSA. And for chemical hazards, for example, we use CHEBI for the URIs. And after those matching process, we derive a kind of RDF format to feed into our graph. And with knowledge graph, we have three objectives in mind. The first one is to build a graph connecting food to their food safety hazards. The second part is to enrich the graphs with more information from the food system. So the node is not only food and their contaminants, but also, for example, where was the food produced and the surrounding factors of the production. And I'm almost there, so it's the last part. So the third goal is to train the models, algorithms to actually to do the prediction task based on the knowledge graph we built from the early stage. So this is still a working process activities. I hope to share some new findings in the upcoming future events for dissemination. Yeah.